Hey guys, my name's Amy and I'm one of the authors of the Spend Permission project. My colleague Connor is the other author and will be monitoring Discord and email for any pings from you guys this week, but I wanted to hop on here and do a quick walkthrough of the code and of the project just to set you all up for success so you can do your best work in this competition. So this project is called Spend Permissions. And at a super high level, the concept of spend permissions is logic that is designed to integrate with the Coinbase smart wallet. So that's Coinbase's, here's the dependency actually. Coinbase's implementation of ERC 4337 account abstraction. So this is a programmable smart contract wallet, and spend permissions allow you to authorize third-party spenders to spend tokens from your smart contract wallet. And we all know that authorization of third-party spenders has long existed via certain aspects of token standards like ERC20 with the approval mechanism for some allowance or like permit-based spending, for example. But the unique thing about this approach and the fact that we now get to work with smart contract wallets is that we can actually start to define and determine any arbitrary set of logic that we want to define that governs how funds or other assets move in and out of smart contract wallets. So this is a much more open-ended, creative space to be designing this in, and it also doesn't have to be a solution that is accepted as an interoperable token standard, because this can be implemented one-off as something that integrates with a smart contract wallet as opposed to having to be native to every single instance of a token standard. So hopefully that helps with a little bit of background. So what is a spend permission? Our version of a spend permission is a bit more nuanced and granular than the traditional basic sort of allowance, in particular because our spend permission is designed to operate in a recurring way. So in that sense, we've basically created a mechanism for a subscription type payment or a recurring allowance. So a spend permission is parameterized by this struct that you can see here. The account is the smart contract wallet that's doing the authorizing. The spender is the third-party account that is being authorized to spend these tokens. The token is obviously what we're authorizing to spend. Note that for native token, so for ETH, we are conforming to 7528, meaning we use this like EEEEEE address. It's right here, native token address. And then for any ERC20, which is the only other token standard we support, then that would just be the contract address. The allowance dictates the maximum allowed value that can be spent, but that's per recurring period. So that resets every time the recurring period's duration has passed. Period dictates the length of that recurring basis in seconds. The start time and the end time dictate when the spend permission becomes valid and then when the spend permission is no longer valid. So you could set these to 0 and then uint48 max, and that would just be a sort of permanently valid spend permission. We'll talk about revoking later. Or you can set this, to a more bounded timeline. And then finally, as we'll see later, spend permissions in our contract are managed by their hash. We don't actually write all of this struct data to storage. So we introduce here an arbitrary salt to differentiate unique spend permissions to lead to different hashes in the case that you have multiple spend permissions that may, in a very valid, earnest way, have identical content, identical data here. And finally, we have a bytes extra data, arbitrary data vector that can be included in the struct that gets signed over. And this can be for the spender, the app, the developer to use in whatever way they may find use for. Okay, so the way that this spend permission manager works is that the Coinbase smart wallet, so the user's smart account, actually adds this contract as an owner of the smart account. So they add this contract in a very privileged way, such that this contract can control the smart account as much as any primary owner or EOA owner. So it's very important that this permission manager can only carry out extremely limited and well-defined actions because of its very privileged position. So let's get into the basic functions of managing spend permissions, and we'll come back and talk about these additional structs a little bit later. So the first step in the sort of spend permission user story is that a spend permission needs to be approved so that the user is explicitly authorizing this third party to spend their funds. So this can happen in a couple of different ways. The first and most straightforward way is that the user themselves, so that's the account, can call approve directly with the details of a spend permission struct. And what that does is it sets, first there are a variety of validation and sanity checks in here, so I'll let you guys read those on your own. And then it sets a Boolean in this mapping is approved, which maps from the hash of the permission to the account. Even though it's extremely unlikely that there would be a hash collision, this just makes it explicitly clear whose spend permission is being approved, just so that there's absolutely minimal risk of anyone being able to spend or approve spend permissions on behalf of anyone else. So it just sets this flag in this mapping to true. So the other way that spend permissions can be approved is with signatures. And this is because we want the third-party app, the spender, to potentially also take on the gas cost of performing the approval. So in this way, they're able to simply request a signature from the user and then present that kind of much like permit-style approval would be presented to the contract and create approval that way. So this uses standard like ERC 1271 contract signatures to be validated. But something to go into around this particular approval path, and this will be a bit of a rabbit hole, so get ready. Because we're working with smart contract wallets as the user accounts, it's possible that those accounts haven't been deployed yet, meaning that we know what the address is going to be because it's deterministic with create2 counterfactual addresses. So we actually know what the user's account is, but we may not have actually deployed the smart contract wallet itself. So there's an ERC standard for handling that situation called ERC 6492. We can see this EIP is linked here in the docs. And the 6492 basically specifies a format for including in a signature a wrapper that indicates the init code, so basically the factory and the call data that you would pass to that factory that would be needed to deploy the actual account that corresponds to the account that's doing the signing. So what this signature validation is actually doing is it's validating the signature, but it's possible that that signature has a 6492 style wrapper on it, meaning that the account actually needs to be validated as well. Or, needs to be deployed as well. So originally, we created an implementation in which this spend permission contract was performing this deployment. However, because this ERC 6492 format basically allows for an unchecked vector and an unchecked arbitrary target and call data that rides in on the 6492 signature, it meant that this highly permissioned spend permission manager contract could be triggered into making an arbitrary call, including calling into the smart contract wallet that it's an owner of. So that's a severely critical vulnerability, and if any of you end up reading our most recent audit report, you will see that vulnerability described in detail. So the solution we've settled on is to actually create a separate dedicated contract. So that is what we've called the public ERC 6492 validator. And we delegate out the signature validation to this unprivileged contract. So it can attempt to call the factory, deploy the contract, and eventually get around to actually validating the signature with that freshly deployed contract in a totally unprivileged environment. So this is a new pattern. We don't believe it's vulnerable, but this is something that we are hoping survives the competition and future audits and maybe a vulnerable aspect of our code. So please look carefully at this. While we're here, another thing I'd like to point out is the fact that we are using Solaidi's signature checker lib because he has a super gas efficient implementation of the various paths of this ERC, but we don't believe that this library has been audited formally yet. So this code in the signature checker lib is also fair game. And just like something we would love you to take a look at, specifically the two functions that we make use of. Okay, I think that's most of the 6492 stuff. We'll see if we come across anything else. Okay, so back to approving with a signature. So we perform our check, we potentially deploy the account if necessary. If the signature is not valid, we revert. If it is valid, we again call the same inner approve method. And I guess the last thing to note about approving with signatures is that we're also offering this in a batch format. The idea behind this is that we would like to be able to, depending on the use case of the app or the spender, they may need to spend a couple of different tokens from the user, and it would be cumbersome if each one of those permissions required a separate signature, because that's a lot of clicks for the user. So this is a way to approve a batch all at once if it improves user experience. And the main aspects of this approach that could probably use some scrutiny would be around properly serializing, basically properly hashing the batch object in accordance with EIP 712, and potentially any considerations just around risks that come with potentially authorizing large numbers of permissions at once. So you'll see up top here that batches are formatted a little bit differently. They involve these two structs, but in a batch, we enforce a couple of shared properties. So the whole batch applies to the same user account and has the same timeline, so same period start end. And then you can specify the individual unique spend permission details with this array of permission detail structs. So unique spender, token allowance, and then of course salt and extra data for uniqueness on a per permission basis. Okay, so once, before we move on to actually like spending and using spend permissions, let's touch on revoking spend permissions. So this one's simple. We just have a function called revoke. The security around this simply requires that the sender is the account, is the user. And the I guess the interesting thing to point out about revocation is that it doesn't actually share the same mapping as the approval bookkeeping. And that's because with the signature-based approvals, it could be possible for a permission or for a user to revoke a permission, but for the spender to hang on to the original signature across that permission and then replay it and reapprove the spend permission. So instead, we keep track of whether that permission has been revoked. Once it has been revoked, it can never be unrevoked. So it'll still be true in the is approved mapping, but because it's true in the is revoked, it is permanently revoked and it can never actually be used. And even if the spender wants to authorize an identical spend permission, that spend permission will have to have a different hash, either by way of having different data or a different salt or something like that. So once a spend permission has been approved, the spender is able to spend that spend permission. So the spend function, this is the only spend function. When it comes to batching, I'll take a quick detour here. If a spender wanted to spend multiple permissions at once, or if a user wants to revoke multiple permissions at once, but we don't offer like batched interfaces for those actions, we're relying on sort of native call batching that is available via the smart contract wallet, which has a function called execute batch. So we only found it necessary to add like one simple spend function, given that you can batch these calls in other ways. So spend does a couple of things. We can look at use spend permission. So use spend permission is basically going to make a couple of validation checks, most importantly being that the permission is approved. It's then going to get the current period data, which is this struct right here called period spend. And this indicates the start of the current period of the recurring allowance that we are in right now, the end time of that current period, and then what the cumulative spend has been thus far. So I won't go into all of the bookkeeping here, but this function get current period, which is also exposed publicly as a getter, so that folks off-chain can understand, what's available to them in the current period. That is called here to get the information about what the current total spend has been. There's documentation about this in the repo that details with examples how this accounting actually works. So I think you should just check that out as opposed to trying to listen to me explain all of that verbally. But it's basically just the intuitive accounting around what period are we in, how much has been spent already, how much do we have left that we're allowed to spend, are we exceeding that, and then making sure that we're tracking the fact that we're currently spending some amount of token. We emit events. And then the last call in spend is the actual transfer. And so this is where we call execute on the Coinbase smart wallet. And depending on what type of token we're working with, we either make an ETH transfer or we call transfer on the ERC20. And again, this is where the privilege of the spend permission manager contract comes into play, because you have to be an owner of the smart contract wallet to call a function like execute on it with all this arbitrary data. Okay, I think that's pretty much it. So again, there's documentation in the repo here. We have, let's close this down. So we have a variety of diagrams on markdown documents describing all of these major flows. We have a dedicated spend permission accounting document here. We also have robust tests. So you'll find that every major or public function has a dedicated test file. And we've set up shared boilerplate across these tests that all of these tests inherit via a base contract, which has a variety of shared state and logic, a spend permission manager base, which has even more esoteric spend permission related basic logic. And you'll see the way that these tests inherit this boilerplate and share a similar structure. So this should be more than enough to get you started with any sort of proof of concept that you need to come up with. And yeah, other than that, this is just a basic Foundry project. So you'll just need Foundry and can install dependencies with Forge install, can run tests with Forge test, and that is about it. So we'll be available on Discord and by email, and would love to field your questions and invite you to do your worst. So good luck in the competition, and thank you so much for your time and attention, and we wish you luck.